these amalgamated importance scores, this vector, I just called it a bold-faced X for ease of notation. All right, that's what the X, the importance scores on the left-hand side look like. X1 equals, X2 equals, X3 equals, X4 equals. I'm just going to use X to stand for the left side of those equations I wrote down. The right side is going to involve something called a matrix, which for us is going to be a rectangular array of numbers. Here's a matrix right here. I typically call them A, just because in this talk that's what I call almost all the matrices, is boldface A. This is a square matrix. It has 4 rows and 4 columns of numbers. And for us, matrices are they're interesting objects. They're very dynamic. They have a lot of geometry behind them. But for us, a matrix is simply going to be a notational trick. A sort of notational way to write down systems of linear equations in a compact form. So, a matrix times a vector. Okay? Those equations that I wrote down that had the right-hand sides that depend on the structure of the web, you know, x1 over 2 plus x2 over 3, etc. Okay? The right-hand side of those equations looked roughly like this. They were linear combinations of the four x's that I was looking for. Okay, I'm going to write them using matrix vector notation. And the way I'll do it is, if this matrix is A, and this is the vector x, then when I talk about the product A times x, what I mean is this quantity right here. And so this matrix here, in some sense, encodes these 4 linear combinations of the x's. 1, 2, 3, negative 1. 1, x1, 2, x2, 3, x3, negative 1, x4. The other 3 rows here simply encode these 3 linear expressions involving the x's here. Okay? So this gives me a very compact way to write down a system of linear equations and not get too emotionally involved in what exactly the linear combinations over here are. They all are embodied in the matrix A, and I can kind of sweep them under the rug until I actually need to do computation. So here, for example, let me show you. There's the 4 equations that came out of ranking our 4 web pages. Okay? If I were to write this in matrix notation, I would write this system more compactly as x, this x here, equals A times x, where A is a matrix that embodies these 4 linear combinations. And there's the matrix here. I call it the link matrix in this case. And of course, why is the first row 0, 0, 1, 1/2? Because this equation is 0x1 plus 0x2 plus 1x3 plus 1/2 x4. So you can think of this as the x1 coefficient, x2, x3, and x4. Okay? This row here of the matrix embodies this top equation here, this linear expression here. The second row of the matrix, 1/3 x1 and no x2, x3, or x4. 1/3 x1, 0, 0, 0 for the other coefficients. And then the other rows have a similar interpretation. So it lets me write these guys down in this very compact form, x equals ax, and all the structure of the web that we're looking at, all the links between the pages, the number of pages, they're all embodied inside this matrix A, and I don't have to think about them unless I want to. Okay? So all web ranking problems are going to come down to finding a solution to x equals ax. The question is, though, what's A and how am I going to solve this system? By the way, check out that matrix there. Notice the columns. You see what they all add up to? They all add up to 1. And that is, in fact, that comes straight out of this procedure. Okay? Without belaboring it, this indicates page 1 through cast 1, it had 3 outgoing links. 1/3 of it went to page 2, 1/3 to page 3, 1/3 to page 4. Okay? This column here, page 2 had 2 outgoing links. So half of its vote went to page 3, half went to page 4. Every entry here has an interpretation as a link from one page to another. The columns sum to 1, because that's the nature of how we divvied up the votes. And, you know, one thing I didn't point out earlier is I could have allowed pages to link to themselves. There's nothing wrong with that per se, but I didn't do that in my example. So there are, like in the x1 equation, there's no x1 over here because x1 is not allowed to link to himself. And that manifests itself in these zeros here, in these diagonal positions. Okay? No pages can link to themselves, so there will always be zeros in that diagonal position. It's another pattern you can observe in that matrix. Okay, now, We're trying to find a solution to x equals ax. I showed you how to do it with the fixed point iteration, but I want to show you what it looks like in matrix notation, and most importantly, why will the fixed point iteration converge to something reasonable in this case? Well, okay, here's a little example that illustrates if you go looking for a solution to x equals ax, there may or may not be an interesting solution to that. It depends on the matrix A. Okay? For example, if A is this matrix, 1, 2, 2, 4, the equation, the matrix vector equation, x equals ax, can be written out in more conventional terms as, here's x, so x1, x2, equals ax, 1x1 plus 2x2, 2x1 plus 4x2. Those are two equations and two unknowns. If you want to solve those, you could instantly convince yourself that there are no interesting solutions. They're all trivial, okay? Because, of course, cancel x1 off of both sides, immediately conclude 2x2 is 0, so x2 is 0. So plug that in here, and plug in 0 for x2, and immediately conclude x1 is also 0. That's the only solution in this case. Okay? So this is an important point. If you write down a random matrix, and you look for a solution to x equals ax, there may or may not be a solution. In fact, for a random matrix, whatever that means, there probably won't be any solution that's interesting. But it turns out, for the PageRank algorithm, there always will be at least one solution that's non-trivial. Okay, now, here's a little terminology. Okay, we've been looking for solutions to x equals ax, or sometimes I'll write it as ax equals x. Okay, a more general version of this problem is find a vector x so that a times x equals a multiple of x. Conventionally, I'd use lambda here, so lambda is just some number. So, for example, a times x equals 1 times x. That's the problem we've been considering for the PageRank algorithm. But a times x equals 2 times x. You could ask whether there's a non-trivial solution to that. Okay, well, if there is a solution to that, if there is a non-zero solution for x here for a given choice of lambda, we call lambda an eigenvalue. That should be an eigenvalue for A, the matrix A. Okay, lambda is called an eigenvalue for A. I'll give you an example with that little 2 by 2 matrix I had a minute ago. Okay, the lambdas, they're just numbers, they're scalars or numbers. Okay, not all choices for lambda will end up being eigenvalues for a fixed matrix A. That is to say, if you give me a matrix A, for most choices of lambda, you will not be able to find a non-zero solution to that equation. In most cases, x equals all zeros will be the only solution. Okay? So in this terminology, that previous example I had where I chose this matrix, and I showed you that ax equals x has no solution, in this terminology, lambda equals 1 is not an eigenvalue for that matrix, because a times x equals 1 times x has no solution, no non-trivial solution. Okay? But for that matrix there, it turns out that 5 is an eigenvalue, because a times x equals 5 times x does have a solution. Okay? This system of equations right now, a times x equals 5 times x can be written out more conventionally as, in this form, a is 1, 2, 2, 4, so 1, 2, 2, 4 equals 5x1, 5x2. There is a solution to that system of equations. Okay? In fact, if you go through, you chase through the algebra here, you'll find that both of those equations boil down to x2 equals 2x1. So any vector you pick that's of the form x1 and 2 times x1, because the second component should be twice the first, anything in this form, in particular, 1, 2, the vector 1, 2, or choosing x1 equals 1 and x2 equals 2, that will provide a solution to this system of equations right here. You can check mentally. 1 for x1 and 2 for x2, this equation is, the first equation is satisfied. And the second equation, 1 for x1, 2 for x2, the equation is satisfied. Okay, so 5 would be said to be an eigenvalue for this matrix. Now bear in mind, for the PageRank algorithm, Google's PageRank algorithm, we are concerned with eigenvalues of 1 for the matrix. But it pays to understand that there could be other eigenvalues for the matrix. So here's a little audience test just to see if you're awake. Here's a matrix, 3, 1, 1, 3, and I claim that 4 is an eigenvalue for this matrix. That is, there is a non-zero solution to ax equals 4 times x. Or if you want to write it out in high school algebra terms, I claim there is a non-zero solution for x1, x2 for this pair of equations here, which is nothing more than ax equals 4x. Now, I'm sure you can see the solution, right? What can I pick for x1 and x2? Okay, I'll give you a hint. Small, yeah, 1, 1. Okay, I was going to say small positive integers less than 2. 1 and 1 for x1 and x2 would satisfy these equations. Although bear in mind, so would 10 and 10, or 912 and 912. Okay, all that matters is, all you need here is that x1 equals x2, and you have a pair of solutions to that equation. Okay, that would be, so 1, 1, 1, the vector x1 equals 1, x2 equals 1, that would be an eigenvector for this matrix with eigenvalue 4. Okay, there is actually, I probably shouldn't even throw this out, there is another eigenvalue for that matrix and corresponding eigenvector, but it's not as easy to see. Actually, I forgot what it is. Good God, why did I say that? I think it's 2. It's 2. Okay, if you replace the 4s by 2s, then 1, negative 1 is an eigenvector as well. You get a solution 3x1 plus x2 equals 2x1, x1 plus 3x2 equals 2x2. 1 and negative 1 become an eigenvector, and with eigenvalue 2. Okay. Anyway, that's the notion of eigenvalues and eigenvectors. Now here's a few facts about eigenvalues and eigenvectors. If A is an n by n matrix, then we say a non-zero vector x is an eigenvector for A if this equation is satisfied. Lambda is the corresponding eigenvalue. That's the definition I gave a moment ago. For a typical n by n matrix, meaning n rows and n columns, like 4 rows and 4 columns, you will find that there are n numbers that act as eigenvalues. Now this is not necessarily the case. There may be, first of all, they need not be real numbers. They may be complex numbers, and there may be repeats. But generically, an n by n matrix typically has n distinct eigenvalues. Okay? And each eigenvalue comes with its own eigenvector. Okay? So, in this case, so that's a little quick tutorial on eigenvalues and eigenvectors. Let's go back to the PageRank algorithm. Here's the web again. Here's what we're looking for. X equals AX. A is the link matrix here that I wrote down a minute ago. Okay, and as I noted earlier, all the columns of A sum to 1. Okay, the terminology here is that A is column stochastic. The columns sum to 1. If the rows sum to 1, you say it's row stochastic. Okay, so there is a theorem here that actually isn't very hard to prove, but unless you've had linear algebra, it's a 3-line proof if you've taken a linear algebra course. If you haven't, well, I'm not gonna. If you're interested, come see me afterwards. I'll show you how to prove it. But a column stochastic matrix always has 1 as an eigenvalue. This is a theorem that you can easily prove if you have some basic tools from linear algebra. In other words, the PageRank algorithm that I presented, which requires us to find a non-zero solution to this, or in eigenvector eigenvalue terms, we need to find an eigenvector for A with eigenvalue 1. It's guaranteed to always exist for these matrices that we come up with where the columns sum to 1. And actually, what's even better is 1 will always be the largest eigenvalue for the matrix. This turns out to be extremely helpful. So 1 will always be the largest eigenvalue as measured in magnitude or absolute values. If there are other eigenvalues, they will be smaller than 1, and if they're complex, they'll have a modulus less than 1. Okay? Our previous method, that fixed point iterative method I showed you for finding a solution to x equals ax, you can summarize it more tightly in matrix notation like this. Okay? You want to find a solution to x equals ax? Well, take a guess at the solution. Just take a wild guess. I'll tell you though, it's helpful well, it's helpful if you take the guess to be non-negative. Okay, I'll come back to that later. In any case, take a guess at the solution, multiply your guess by the matrix A to produce an updated version of your guess, and just keep doing that. Multiply by A, feed it back in, multiply by A, multiply by A. Just multiply by the matrix A over and over and over again. It will converge. In this case, it will converge to a solution to x equals ax. With one little twist. Okay? And this algorithm, when do you stop Well, you stop when the when your iterates stop changing. So in this context, this is called the power method for finding an eigenvector for a matrix. The power method, because what you're doing is basically taking your initial guess and multiplying it by higher and higher powers of A. That's what's going on here. So you're taking x naught, you multiply by A, you multiply by A again, multiply by A again, over and over and over and over again, and eventually the result will stabilize to an eigenvector with eigenvalue 1. Here's a simple example of that in action. This is a matrix A that I made up that is column stochastic. It doesn't correspond to any web, but nonetheless the columns sum to 1. And I took as my initial guess at an eigenvector for this matrix, I took 0.7, 0.3. And then I took that guess and I multiplied it by A. And I multiplied it by A again, and again, and again. And look at what happened after just 4 lousy iterations. Okay? Look at how fast the components stabilized to 0.4 and 0.6. That's because 0.4 and 0.6 are an eigenvector for this matrix with eigenvalue 1. If you take 1/2 times 0.4 plus 1/3 times 0.6, you'll get 0.4 back. And if you take 1/2 times 0.4 and 2/3 times 0.6, you'll get 0.6. X is the same as A times X here. It converges very rapidly here. Okay? So to find the eigenvector you want, you just multiply by A over and over and over again. This is the guts of Google's PageRank algorithm. It's the power method applied to this link matrix. Okay, so it's the ultimately simple brain-dead computation. Why does it work? Well, this is in some sense this is the core of the matrix algebra part of the talk. Why does it work? Well, I could give you an abstract proof, but let me show you for that particular matrix why it works. Okay, this matrix, I told you that an n by n matrix has 2 eigenvectors and 2 eigenvalues typically. Okay, well this matrix has n eigenvectors, not n eigenvalues. So this 2 by 2 matrix, turns out it has 2 eigenvectors. Here they are. Here's one, here's another. The eigenvalue for this eigenvector is 1/6. The eigenvalue for this eigenvector is 1. As I said, 1 is always an eigenvalue for a column stochastic matrix, and all the other eigenvalues will be less than or equal to 1. In this case, 1/6 is one of them. Okay, so what would happen if I took a random vector, a 2-dimensional vector, and multiplied it by A over and over and over again? Why will it converge to something that looks like this, the eigenvector I want? Well, okay, you give me any vector x naught a, b, as long as it's non-zero. If you give me any vector x naught a with first component a, second component b, I can write it as a linear combination of these 2 vectors here. I can write it as something times this vector plus something times this vector. The somethings are unimportant, but if you care, here's what you should pick for the coefficients c1 and c2. But really, this is all that matters. I can express the initial guess as a linear combination of those two eigenvectors. Okay, now, I got a typo here. That should be x naught, okay? If my initial guess can be written as a linear combination of 2 eigenvectors, okay, well what happens when I multiply x naught by the matrix A? Well, I produce my next updated iterate, x1. It's going to be, you take this stuff times A, you're going to get exactly this. The constants can filter in and out of matrix multiplication. I'm going to get C1 times AV1 plus C2 times AV2. But A times V1 is 1/6 V1. V1 is an eigenvector, so when I multiply it by A, I simply divide it by 6. V2 is an eigenvector for A with eigenvalue 1. A times V2 is V2. So when I multiply x1, I'm going to multiply x naught by A to produce my updated iterate, x1. This is what I get. Now, do it again. Produce the next update, okay, x2. Okay, x2 is A times x1. Well, A times x1 is, if you look at, here's what x1 is, multiply this expression by A. You're going to get C1 over 6, AV1, plus C2 times AV2, but AV1 is 1/6 V1. So I'll take that 1/6 and I'll put it down here, C1 over 36. AV2 is V2. So this is what I get when I multiply my initial guess by A twice. And it's pretty easy to see what goes on if I continue this process. If I multiply x2 by A, it's going to result in a 6 cubed down here, C1 over 216. This term will just sit there rock solid, unchanged, because A times V2 is V2, over and over and over again. This is what it looks like. Well, look at what happens as you take k to infinity. This term is gone, and it says that your kth iterant is going to be a multiple of the eigenvector V2, which is the eigenvector we want. It's the eigenvector with the eigenvalue 1. So we'll end up with some arbitrary scalar multiple of it. And I don't care, a scalar multiple is as good as anything else, as long as it's non-zero. Okay? This is the gist of why the power method works. In a larger example, where there are 10 billion eigenvectors and 10 billion eigenvalues, as long as the largest eigenvalue is 1 and all the others are smaller, it'll work. And with enough iterations. Okay? Now, here's some properties you would like the eigenvector to have, because you're going to use its components to score how important the web pages are. You'd like it to be non-negative. It turns out, it always will be. You can prove that. You'd like it, pardon?
Wow.
Yeah, it's, well, yeah, it is kind of curious, isn't it? You'd like it to be unique up to scaling. You'd like that procedure to converge to something that's unambiguously converge to something, and that you can use to rank web pages. Well, actually, this is not guaranteed unless you make a small modification here. And of course, you'd like this scheme to be easy to implement for a 10 billion by 10 billion matrix. Well, okay, here's something that breaks this scheme. Okay, this is a web of 5 pages, and notice how it breaks into 2 distinct components that don't interact with each other. Here's the matrix A that you get, this link matrix, and it's got this kind of blocky structure. The upper 2 by 2 block here corresponds to these 2 guys. The bottom 3 by 3 block corresponds to these 3 guys. And of course, these big blocks of zeros indicate that none of these pages link to any of those pages and vice versa. If you compute the eigenvectors here that have eigenvalue 1, solutions to x equals ax, you find there are really 2 distinct eigenvectors. There are actually infinitely many, but they all come, in some sense, they're represented by these 2 pieces. And these 2 guys, they're completely distinct, independent eigenvectors, linearly independent in the language of linear algebra. This one is in some sense ranking these 2 pages as importance 1/2 and importance 1/2, and these guys are all zeros. Well, that doesn't seem quite reasonable. I don't think this is a good choice to use. This eigenvector is ranking these 2 guys as 0 importance, these 2 guys as 1/2, and this guy is 0, which makes sense for this subweb. Nobody links to him, so he gets a 0. But they're each ranking in some sense these different components. So you need somehow to put these together to find an overall ranking for the web. Well, which one should we use? And here's a general theorem. If your web has R components, if you consider it as a graph, R distinct components, then this problem will be R-fold worse. There will be R independent eigenvectors with eigenvalue 1. So the problem will be even worse. How do you fix this? Well, the core problem here is that we've got disjoint components here where pieces from here don't link to pieces from here and vice versa. The way we get around this is we alter our web in by adding fake links from each page to every other page, but we make them weak links so they don't distort the web structure. Okay, what we do is this. Okay, we're going to give every page on the web a fake weak link to every other page, and the way we're going to do it is this. Okay, that original link matrix A is going to be replaced by a new matrix M, which is going to be a weighted combination of the original link matrix A and a new link matrix X that I call the egalitarian matrix. This is the matrix you would write down for a web where every single page links to every single other page, even to themselves. The matrix S would look like this. So what we're going to do is take a blend, a tunable blend of the original link matrix and the egalitarian